All right, guys, Mr. Antonucci here, and in this video, we're going to talk about linear approximations. Local linearity is the concept that the tangent line can be used to approximate function values near the point of tangency. So if I have the graph of a function f of x, and I have the point C and the y value f of c, the tangent line to the graph at that function at that point is very close to the graph of the function at that point for points close to that point. So if I circle a small neighborhood of points near that point, then the tangent line is a good approximation. So it's important to understand how to determine this, if this approximation is an under or overestimate of the actual value. The shape of the graph near the point of tangency is what determines this. If you look at the graph that I drew, the graph is considered to be concave down at that point, which means the graph is curving downward. So the tangent line rides on top of the curve and it's going to give overestimates. If we had a function that was concave up, meaning it's curved upwards, the tangent line is going to ride underneath the curve and it's going to give underestimates. Often on the AP exam, you'll be asked to determine this for an approximation. But be careful, don't confuse the concavity with increasing or decreasing. For example, if I have a parabola that opens downward, any point that I pick for the line of tangency, say here or here or here, will overestimate the true values of the function near the point of tangency, because no matter where I put it, the tangent line is going to ride on top of the curve. Similarly, if I have a graph that's always concave up, like an upward opening parabola, no matter where I put the tangent line, it's always going to ride underneath the curve, and therefore if the tangent line is used to approximate values of the function, they were going to under approximate it. Now, a couple more things. The linear approximation, we'll call it L of x, to a differentiable function f at x equals c is given by the following function. L of x equals f of c plus f prime of c times x minus c, where c is the point of tangency. The closer the x value is that we want to approximate that it is to the c value, the point of tangency, the better. When the tangent line is above the graph, the approximation is an overestimate. Also, when the tangent line is below the graph, the approximation is an underestimate. The graph of L of x is called the local linear approximation of f near c. Another way to think about this is y equals y1 plus slope times x minus x1. This is just point slope form solved for y, but given in function notation. In this case, the point of tangency is c comma f of c. The slope is the derivative evaluated at c. Let's look at an example. We want to find the linear approximation L of x to f of x equals sine x near x equals 0, then use L of x to approximate sine of negative 0.3, sine of 0.1, and so forth and so on. And then we want to graph the original function and its tangent line approximation on the same graph. So in this case, x equals 0 is the point of tangency. That's what's playing the role of c in our local linear approximation. So I need to figure out f of 0, which is 0, sine of 0 is 0. So that means my point of tangency is 0, comma 0. Then I need to figure out the slope. The derivative of sine is cosine x. Then the derivative evaluated at that point is going to be 1. So L of x is equal to f of c, which is 0, plus f prime of c, which is 1, times x minus c, which is 1. So L of x just simplifies down to 1x, or just x. That means the line y equals x is the tangent line. Then I want to approximate sine of negative 0.3. Sine of negative 0.3 is approximately equal to L of negative 0.3, which is just x, so negative 0.3. Sine of 0.1 is approximately equal to L of x evaluated at 0.1. Since L of x is just equal to the x value, that's going to be 0.1. In fact, as we keep going here, the pattern in this case is that the tangent line approximates the value of sine to be equal to the x value for points near x equals 0. So sine of 0.4 would be approximately equal to 0.4. Sine of 0.5 would be approximately equal to 0.5, and sine of pi over 4 would be approximately equal to pi over 4. So let's go and take a look at the graph. So here's the graph of sine x. If I zoom in pretty close to x equals 0, I can graph the local linear approximation. One thing I want to point out here while we have the graph is notice that as I zoom in closer and closer to that point of tangency, the graph of sine starts to look like a linear function near x equals 0. But if I start zooming out, you can begin to see more of the curvature and how it deviates from that. I'm going to highlight the point of tangency right here. And then what I'm going to do is we can have the values of L of x. So we wanted negative 0.3, 0.1, and so forth and so on. We could go down the line there. Now, this next thing that I have right here is what we would call the error. It's the absolute value of the difference between your approximation and the true value. So if x is equal to negative 0.3, the difference is 0.0047. If x is 0.1, well, this would be 0.000166583. Now notice this, as I get further and further away, 0.2, the error is becoming a little bit bigger and bigger and bigger each time. If I try that pi over 4, which is approximately 0.7854, notice the error gets even bigger. If I go all the way to pi over 2, gets bigger, pi is going to get bigger and bigger. And you can see over here on the graph that as I get further away from the point of tangency, the error is getting bigger. That's what these points are here. Graphically, the error is the distance between the tangent line and the curve for that specific x value. For this example, we have the function f, but all we know is its derivative is 3x squared minus 1, and the point f of 2 equals 8. We're going to use the linear approximation L of x to f of x in order to approximate f of 2.1. Remember, we need a point and a slope to write the equation of a tangent line or the linearization. Since f of 2 equals 8, that's the point 2 comma 8. And we can plug 2 into the derivative. F prime of 2 is 3 times 2 squared minus 1, which would be 11. So L of x is equal to f of c, which is the y value, 8, plus f prime of c, which is 11, times x minus c. C itself was 2. So this simplifies to 11x minus 14. So f of 2.1 is approximately equal to, I'm using the wavy equal sign to indicate it's approximately equal to L of 2.1, 11 times 2.1 minus 14, which is 9.1. So we would say that f of 2.1 is approximately 9.1. Now, in this case, I just want to point out, I used wavy equal signs here because the true function value is approximately equal to the L of x approximation. Then I used equal signs here because this is representing evaluating the linear approximation function. Then my final answer, I used the wavy equal signs because the 9.1 is approximating the true value of f of 2.1 and not the exact value. Here's another way you may see one of these problems come up. Suppose y equals f of x is a differentiable function. You have values of the function and its derivative in the table, and we want to approximate f of 2.9. That means that the c value that we want to use is the value in the table that is closest to 2.9, which is going to be 3. So we would have the point 3, comma, f of 3, which is negative 8, and then f prime of 3, which is -2. So our linear approximation is going to be the y value plus the slope times x minus the c value. Since the slope was -2, I wrote that as subtraction. And then L of 2.9, you can distribute this and simplify the equation or just plug in 2.9. Notice 2.9 minus 3 is -0.1. So this would be -8 plus 0.2, which is -7.8. So at the end of the day, we would say that f of 2.9 is approximately equal to -7.8. Here we want to use a linear approximation to estimate the value of root 51. In order to estimate this, we need a function that makes sense in this situation. Typically, it's going to be whatever's operating on the number. In this case, we're going to use f of x equals the square root of x. And our point of tangency, the c value, we're going to use something that logically makes sense. In this case, we're going to use 49 because we know the square root of 49. It's the closest perfect square to 51. So f of 49 is square root 49, which is 7. So that means our point of tangency is 49 comma 7. Then f prime is 1 over 2 square root x. So f prime of 49 is 1 over 14. Then we can write the equation of the tangent line. So L of x, remember, your linear approximation is just the equation of the tangent line at that point. So that's going to be 7 plus 1/14 times x minus 49. So square root 51 is approximately L of 51, which equals 7 plus 1/14 times 51 minus 49. 51 minus 49 is 2, so you would have 2/14 or 1/7, which is 50/7. Now, 50/7 as a decimal is 7.142857. Square root 51, rounded to 3 decimal places, is 7.143. Notice if we round this to 3 decimal places, we get the same value. So our approximation is very, very good. So here I have the graph of the square root function, the point of tangency, 49 comma 7, the value of the derivative, and our equation of the tangent line. If I evaluate L of 51, I get the value that we had originally. If we evaluate the square root of 51, we get the decimal value of square root 51. And I just want to show you if we go a little bit further, like L of 60, for example, you get 7.785. If I take the square root of 60, still kind of close, around 1 decimal place, but my accuracy is less. If I go all the way out to 100, well, we know the square root of 100 is 10. I'm off by even more. And you can see if I use 49, this point right here, as my point of tangency, the further away I get, the more the tangent line deviates from the square root graph in either direction. So if I get closer to another perfect square, like 100, I would use the tangent line at that point. I also realize I wrote the wrong number down right here. It's 7.141. So here's an ACE-P style question. Let f be the function given by f of x equals 3x squared minus 4x plus 2. The tangent line to the graph of f at x equals 1 is used to approximate values of f of x. Which of the following is the smallest value of x for which the error resulting from this tangent line approximation is more than 0.5? First thing to do is get our tangent line approximation. So the x value we're using is x equals 1. So f of 1 is going to be 3 minus 4 plus 2, which is 1, which means the point is 1 comma 1. F prime of x is 6x minus 4. So f prime of 1 is 2. We can write the linear approximation L of x which is y plus the derivative times x minus 1. So that's going to be 2x minus 1 is our L of x. And now the error is the absolute value of the difference of L of x and f of x. We want to know where the error is more than 0.5. So here I have the graph of f in red, the graph of L in blue, and I have a table of values for finding the error. So I'm going to plug in the different x values, 1.3. So the first one that's greater than 0.5 is 0.75, which is the x value of 1.5. So this is the smallest x value for which the error is greater than 0.5. Choice C. All right, guys, that's it for linear approximations. Hope that was helpful to you. Make sure you subscribe to the channel, like this video, and drop me a comment. Let me know if that was helpful to you.